Welcome to the lectures for the third part of our course. The first part of our course was on first-order logic and its meta-theory. Second part of the course was on modal logic. This third part of the course will focus on alternatives to standard first-order theory. These alternatives are not the same kind of logical system that we studied when we studied alternatives to first-order logic, such as free logic, intuitionistic logic, and the like. These are ones that replace the strong consequence relation of first-order logic with a weaker consequence relation. So this first lecture will be about the topic of non-monotonic logics, as they are called. So first we'll talk a little bit about what non-monotonicity is and how probability theory is going to play a role in the story of the approach to non-monotonic logics that we are going to be studying. So for this talk, I will talk just about non-monotonicity, and in the next lecture, we'll start talking more particularly about probability theory. So first, concerning non-monotonicity, the first-order system that we studied is a deductive system. And in a deductive system, the support from the premises to the conclusion is total. In any scenario in which the premises are true has to be a scenario in which the conclusion is true as well. In fact, that's how we define the notion of soundness, or validity in this case. Soundness requires that the premises actually be true as well as the argument itself being valid. So the support is total. In non-deductive systems, the support won't be total, it will be partial. Even if the premises support the conclusion, there can be scenarios in which the premises are true and the conclusion is false. So for example, one thing that we're going to study is lottery situations. And suppose you have a lottery system where you buy up a whole bunch of tickets, thinking the lottery payoff will be big enough. In fact, there's one of the lotto prizes, I think it was in Massachusetts, worked this way, that the face value of the ticket, the value of a ticket came to exceed the face value of the ticket if the purse became large enough. So as they would do drawings and nobody would win, then the purse size increases. And it got to the point where the purse size was big enough that the value of each ticket was 3 or 4 or 5 times, maybe even more than the face value of the ticket. And there were 3 people that pooled their money, bought up a whole bunch of money. One was a math professor and one was a statistician, and I can't remember who the third one was. Bought up a huge number of tickets. They pooled together over $1 million. And in the course of a month, they bought up as many tickets as they could get, and they ended up winning $2.2 million. You had to know something about game theory in order to find out that the face value of the ticket was lower than its actual value in the lottery. And these 3 people figured that out. I don't know if they still run lotteries that way. I suspect somebody got smart and they quit doing it. But in any case, the point is that the support is partial. So suppose there's 10 million tickets available in the lottery and each ticket costs you $1, but the payoff for the lottery is 50 million to the winner. Well, you can't buy every ticket, but suppose you pool your money and you buy as many tickets as you possibly can. Suppose you buy 60% of the tickets. That doesn't guarantee that you're going to win, but you now have information that supports the conclusion that you will win. It doesn't support it very strongly, but it supports it more than a 50-50 even chance of winning, and certainly more than just buying one ticket and counting on the odds working out in your favor. So in non-deductive systems, the support is partial. Because of this, deductive systems are said to be monotonic, since the total support from P to Q never changes. If P narrows down the total scenarios to cases where only Q could appear, not Q never appears, then that stays the same no matter what further information we add to P. You can add any future learning you want, and Q will still be supported to exactly the same degree as it was before you learn that new information. And that remains true even if you learn the opposite of P. Because remember, from P and not P, absolutely everything follows. You can prove anything you want from a contradiction in 2 steps. So the support never changes. The language here, if you think about somebody who's a monotone singer, for example, what is it to be a monotone singer? Well, you won't make much money singing, that's for sure. What makes you a monotone singer is you sing the same note no matter what. It never changes. You just stay on that one note. That's the way the support goes from P to Q. Regardless of what else is known, regardless of what else might be learned, the support stays constant. Non-deductive systems are thus non-monotonic, since partial support can disappear once you learn new information. So take the lottery case again. Suppose you do buy up 60% of the tickets, and then you find out that the winning ticket would have to start with the number 9, and you bought no tickets at all that start with the number 9. Now you no longer have 60% confidence levels that you possess the winning ticket. Now you go to 0% confidence levels. So the support disappears in the face of additional learning when it comes to non-monotonic systems or non-deductive systems. Now, why would we be interested in non-monotonic systems rather than just monotonic ones? The answer to this is that the motivation for the study of logic always begins in epistemology. For we want some account of when our inferences are going to be rational ones, when our evidence supports one view rather than another one. And logic is supposed to inform us something about that. Such a motivation would lead you to identify logic, maybe to think of logic as theory of inference, when you're supposed to infer one thing from another. And the modeling in question is likely to make the paradigm case of inference one in which you come to believe some things on the basis of believing other things. So the theory of inference would naturally be thought of as moving from one belief or set of beliefs to another belief or set of beliefs. Yet in our study of logic, we don't start there. We begin with sentences or propositions, the kinds of things that could be believed, but need not be believed. We just start with a non-psychological notion that is purely linguistic or semantic in nature rather than psychological. The reason for this is logic really isn't the theory of inference. Logic isn't the theory of inference, but it's rather a theory of logical implication or consequence relations. And that's a relation that holds between sentences or propositions. Even if inferences are things that occur between beliefs, the theory of logical consequence or logical implication isn't. It's an abstraction away from the psychological material. Even so, the connection remains. We want there to be some connection linking the theory of appropriate inference with the theory of logical consequence. We can call these norms if we want. What is it for you to obey the norms that link the theory of inference with theory of implication? Any such linking principles relative to monotonic systems will link sentences or propositions with beliefs or some other psychological element. The reason for this is the connection between the premises and conclusion is total. So there could be no question of what degree of belief to form or what belief to form on the basis of believing the premises. If our system isn't monotonic, however, we have options to consider since the support relation is only a partial one. So how are we supposed to model this notion of partial support? One possibility is to construct a system that models partial support relative to a given system of information at a time and allows conclusions supported at one time to be retracted later as new information enters the system. You can then think of the such a link as a theory of partial support with a theory of inference being, I'm sorry, I misread that. One can then link a theory of partial support. The partial support is relative to a system of information at a time. You can link that to a theory of inference by taking the system of information to have some connection to actual psychology. So abstractly considered, you can have a system of information that you just specify however you want. You can list a bunch of claims about the world, say, that's my system of information. You can consider another system of information, just the theory of quantum mechanics. That can be your system of information. Your system of information can be anything you want. But if you're going to link to the theory of inference, presumably you'd link to something that has psychological reality. Maybe it's the system of everything known by a given person at a time. Maybe it's the system of everything believed. Maybe the system of everything of which a person is certain. You can even do this in terms of communities. Maybe there's such a thing as common knowledge. So maybe the system of information is the system of common knowledge. It doesn't matter. And then you can define what it is for the conclusion to be something that a person can legitimately infer from a relevant system of this sort, one that has the kind of psychological reality that you think would be crucial for defining these norms, linking the theory of implication with the theory of inference. We can then engage in a bit of meta theory about such systems. In particular, you can ask what makes such system a logical system, one that has the notion of logical consequence as its target. Note as well that the linking principles here link sentences or propositions with beliefs as before, and you might think that there's more to be modeled here than that. I gave some hints. You could talk about common knowledge, group knowledge, community knowledge, community belief. You could also talk about degrees of belief, how strongly a person believes one thing rather than another. So we might want to model not only the support relation between premises and conclusions, but when the support relation is partial, we might also want to model how strong a support is offered, the conclusion by the premises. So if you're just dealing with monotonic logics, you start with P and your only question is whether it's possible for Q to be false while P is true. If the answer is no, and you believe that P is true, then it looks like you're committed to believing that Q is true. But if the support level is partial, as in our lottery case earlier, should you believe that your ticket, that you own the winning ticket? There's a 60% chance initially that you own the winning ticket, but should you believe it? You might think, well, no, that's not the right thing to say. Maybe what you should believe is that the probability of your winning is 60%. That's to make the content of the belief one that encodes the degree of support relation. Another one is to say the strength of your belief, if we model it ranging between 0 and 1 inclusive, the strength of your belief should be at the 0.6 level. Your degree of belief that you own the winning ticket should be 0.6, which of course could obtain and you not actually believe that you own the winning ticket. So there's lots of options here about how to connect non-monotonic logics with the degree of support relation, but we have to say something. We will want to model in some way how strong the support offered the conclusion by the premises is. We don't want merely an on-off switch as we used with monotonic logic. Some people use the language of binary, digital and, which is a binary notion. A digital switch is either on or off. An analog switch comes in degrees. So you can say monotonic logic is digital. Non-monotonic logic better be analog in some way or other. To do this, we need a measure of degree of support. And though there's no compelling reason that we have to do it this way, it's natural to use probability theory. The reason it's natural to do so is because it does give you a gradable notion of support between premises and conclusion, or between one claim and another claim. And second, it's a well-developed, well-defined mathematical theory. So You don't have problems messing around with material that's not well understood in the formal sense. So that's what we are going to do. Now, this is not the only approach to non-monotonic logics. There are a number of different approaches. Here are some that you could do. Instead of using probability theory to model degrees of support, you might use Dempster-Shafer functions. You might use the possibility functions of fuzzy logic that were first developed in the 50s through the 70s and into the 80s and 90s. And there's also ranking functions from Spohn in 1988, and he's been working on that project ever since the 80s. Had a recent book come out on it. So there are alternatives to using probability theory, but it's the simplest approach since probability theory is a fairly common mathematical theory that we all know a little bit something about. So what we're going to do is understand the partial support relation as a probability. The support given to Q by P is represented this way. PR Q slash P, where PR is a probability function, and we read this formula as the probability of Q given P. Now, it's important that we understand that PR is a probability function. The precise degree of support will be related by this conditional probability. And there are multiple possibilities for measuring such support, but we'll just leave open the precise way to measure degree of support. We're just going to start with conditional probabilities, and somewhere along the line, we'll say something about what the measure of support comes to, given the probabilities that we've already learned something about. So PR is a probability function. What is a function? That's the first function. Function is a mapping from one thing to another, the first called the domain and the second the range, where for each element of the domain, there's exactly one thing in the range. So you could have a function that maps, say, the whole numbers onto the odd numbers. You start with the first whole number, and you map it onto the first odd number. You take the second whole number, map it onto the second odd number, and so on. What's important is that there can't be two values for the same element of the domain. So if you take the number 3 and you have described a mapping from 3 to something else so that sometimes it picks out the number 7 and sometimes it picks out the number 11, then the mapping that you're describing is not a function. A function has to generate a unique value in the range given any particular input in the domain. In the case of the probability function, we'll stipulate that the mapping is from sentences or propositions to the real number line between 0 and 1 inclusive. We write that like this, if you're not familiar with that notation. That means the lowest probability any sentence could have is 0. The highest it could have is 1. That completes our general introduction to why we're going to talk about probability.